Now we start with the state space representation. In this we will study introduction, definitions related to state space representations, mathematical representation of state space, guidelines for state space representation and some example. Now coming to introduction section. In last class we have seen the advantages of state space approach over the classical approach, and here we have seen that in case of classical approach we are representing model in terms of transfer function. Transfer function Laplace transform output to Laplace transform input, initial condition tending to 0. Now here state space form, when state space is coming, how to represent the model. So most important point is that in case of state space model we have input, output, and let us say this is a box, and in this particular box there are some states are present, some information is present, and that information is to be utilized to get the proper output. That means here in case of state space we have input and some information in the box. So that information is the box, I am saying that it is called state space, because that information will provide output along with the input, whereas if you say the classical approach, this box, the thing in the box, it is a black box, applying input and getting output. Now thing is that how to select the variables, because in the box there are number of variables are there. For example, suppose last time I have given an example of a doctor, and the patient is goes to doctor, and doctor is saying that you have some problem in the eyes, so we can go for some test relating to eyes, but patient is saying that no sir, I have to do the heart test. That means heart test means that more variables are required. So that means we have problem in the eyes, but you are testing a heart along with the eyes. Actually there is no problem, but we are taking the more variables. But state space say that no, state space say that you take variables which is actually required, do not take much. Another example I can say, suppose say our head of department ask student coordinator of each class to attend the meeting. So let us say there are first year, second year, third year, fourth year, the 4 students have been approached to head regarding the meeting, but there is another student, they are saying that okay, they also want to come, but although they can come, but the main purpose that 4 representative can solve the problem, whatever the discussion will taken place in a meeting or held with the students, with the student representative, they can convey the message. But another is coming, it means that although he can come, but that naturally we cannot require this one. So therefore when the state is that we should be confined to minimum one which can govern the performance of the systems. Therefore the state is nothing but that has some stakeholder in that particular system, and based on that information along with input we can get the outputs, and there are different states are possible. So x1, x2, xn, so they have been present in terms of a vector, that is called state vector. So I read the definition properly. How to define the state? The state, the concept of state is related to minimum set of variables, that I have told you that your variable should be minimum, it should not be more. These variables are called as state variables. Thus the state of a system is defined as the minimum or smallest set of variable such that the knowledge of these variables at t equals to t naught along with the knowledge of the input for t greater than or equal to t naught completely determine the behavior of the system for any time. That means your output depends upon not only on the input but also on the internal state of the system. So that is called state. Now state vector, if n state variable represents behavior of a given system, then n state variable can be considered as n component of a state vector x. Such vector is called a state vector. That means as I told you that when there are many state vectors, say x1, x2, xn, so combine it become x, so x1, x2, x2, xn, that is called a state vector. Now state space, the n dimensional space whose coordinate axis consists of the x1 axis, x2 axis and xn axis is called state space. Now representations. Now as I told you that this is a plant, nth order systems. Now the inputs are coming, see here input signals u1, u2, ur, then this is output y1 up to ym. So, m is the output, r is input, and this is the nth order system, and this system there is a involvement of states x1, x2, xn. So, from this we can also define a state equation. It is the set of n simultaneous first order differential equation with n variables, and output equation it is the linear combination of the state variables and the inputs. Now again I am giving the same diagram. Now here again input variables u1 to ur, y1 to ym, and state variable x1, x2, xn, output variable m, input variable r. So here their state vectors we can represent as x. So here states are n. So we write x1, x2, xn as n cross 1. Input vector r cross 1, that is u1, u2, r, and output vector m cross 1, y1, y2, m. That means m indicates output, r indicates input, and this n indicate the number of states. That is for we considering for the MIMO system plant. Now we have to represent these equations. So here in state space we have to represent in a first order differential equation form. That means here we will find that the first order equation, so dx1 by dt equal to x1 dot t, which is a function of x1, x2, xn, u1, u2, urt. That means x1 dot function of all these variables. Similarly, if you take x2 dx2 by dt, that is x2 dot t, which is also a function of x1, x2, xn, u1, u2, urt. Similarly, dxn by dt, that is equals to xn dot, it is also a function of x1, x2, xn, u1, u2, urt. Finally, this is represented as x dot t equals to function of x u t. Now similarly the output equation is also a function of x and u, therefore it is represented as y1 t equals to g1 function of x1, x2, xn, u1, u2, urt, y2 t equals to g2 function of x1, x2, xn, u1, u2, urt, and finally ymt. So m is the output, as I told earlier, function of gm x1, x2, xn, u1, u2, urt. So that is state equation, it is output equations. As I told you earlier also, the most of the systems are non-linear. Sometimes we have to represent in a linear form, that is called state space form, or in that means we are discussing state space form. That means whatever is the equations, suppose if you write in terms of linear time invariant system form. So here this can be written as, that is in this case each state variable now becomes a linear combination of the system state and the input, that is you have x1 dot equals to a11 xn, x1, a12 x2, a11 xn, b11 u1, b12 u2, b1r into ur. So this is nothing but, they are nothing but the special case of general time invariant system, that is a linear time invariant system form. So here we write xn dot equals to a of n1 x1, a of n1 x2, a n1 xn, b1 un, bn2 u2 and bnr, and therefore in vector matrix form it is written as x dot equals to ax plus bu, where this A we call system matrix and where B is your input matrix. So x dot equals to ax plus bu, this is your state equations. So whatever the elements in A we write down, we have written like this: a11, a12, a1n, a21, a22, a2n, then a1, an to an, and B is also of form n into r form, b11, b12, b1r, b21, b22, b2r, then bn1, bn2, bnr. Now coming to the output equations, as output is also a combination of your input as well as state variables, therefore we have also written output in terms of c11 x12, c1n xnt, D11 UNT DNR. Similarly, we can write Y2, Y3, and finally we reach as output is YUM. So, we are written YMT equals to CM1 X1T, CMN XNT, DM1 UNT, DMR URT. That is YT, Y of t equals to Cx of t and du of t, and the elements, that the coefficients are C11, C12, C1n up to CM1, CM2, CMN, then D11, D12, D11n, D21, D22, D2n, DM1, DM2, DMR. So, here y equals to Cx plus du. So, C is nothing but your output matrix and D is the coupling between input and output. So, the final state space model is x dot equals to Ax plus Bu, y equals to Cx plus du, and as I told earlier, A is system matrix, B is input matrix, C is output matrix, D is coupling matrix, coupling between input and output. And you know, in future we will learn the stability issues, performance, we will see the importance of each matrix A, B, C, D. Right now you only understand that this is the state space model and these are the significance of A, B, C, D. As I told, A system, B input, C output, D is the coupling. Now we have to represent this system in terms of block diagram, that is, now your system we have to represent at x dot equals to Ax plus Bu, y equals to Cx plus du. Now this system we have to represent in terms of block diagram. Now here x dot, that is first order differential equation. That means one thing is clear here, that whatever may be the order of the system, state equation always first order, whereas if you see the transfer functions, this is not possible. You have different order system, 6th order, 10th order, 100 order, but here is true that whatever may be the system, your order is always 1. Therefore, definitely we have to use how many indicators? We have to use only one integrator. So, therefore, here I am using only one integrator here. Now, here one integrator I have used. Now, here I wrote summation block. Now, here x dot, and now if you integrate it becomes x. Now, x dot equals to Ax, this x dot equals to Ax plus B into u, this is B. X dot equal to Ax plus Bu, and what is y? Y equals to here, this is y, I can say this is y equals to Cx, and now here du, so here I can conclude y equals to, this is y, this I can say this is y equals to Cx plus du. So, this is a block diagram representation of a state space model of a linear multi input multi output systems. X dot equals to Ax plus Bu, and what is y? Y equals to Cx plus du. Now, the selection of state, this is very much important in state space analysis. Which state should we take? So, general logic has been given here to select the state is that we have to select the state which has energy storage elements. So, whenever the problem come to you, you have to see that how many energy storage elements are there. So, number of energy storage elements equals to number of states. So, that means that if you select minimum energy storage element, the energy storage element, that means that there are always minimum one. So, here first point is that number of state variables should be minimum. Number of state variable must be linearly independent. It means that let us say Vr equals to I into R. Suppose someone has selected Vr as the state variable, but Vr is dependent on I, so we cannot select I as the state variables. Similarly, if you write x3, x2 plus x5, that means that if you select x3, then we cannot select x2 as the state variable. That means number of state variable must be linearly independent. Then third point, the number of state variables is equal to number of independent energy storage element. As I discussed earlier also, that is whatever be the variables equals to state variables are equal to the number of independent energy storage element. Fourth point, number of state variables equals to the order of the differential equations. That means you have differential equation when we write in terms of Laplace form, that is in transfer function form, that is when I am writing down ys equals to us equals to 1 upon s cube plus 2s square plus 5s plus 1. Now here order is 3. It means that in your actual system in state space you have selected 3 as a state variables, and number of state variables are equal to number of integrators. That means that if you select 3 state variables and they are in terms of let us say x1 dot, x2 dot, x3 dot, that means that is equals to the number of integrators. Now we will see the example, and through example we will see how to develop state space model. And one thing is clear, finally my model we required in terms of x dot equals to ax plus bu, y equals to cx plus du. This model we want. So in order to understand it properly, I am taking a very simple example, that is we have studied in the first year of electrical engineering, that is simple RLC circuit. So I am drawing a simple RLC circuit. So I am writing down RLC. This is simple circuit. This is input Vi, this is R, this is L, and this is C. I can write plus minus here, then this is input Vi, Now assume that this is one current is flowing through circuit IL. Now we have to write, and as I told you that our purpose is to develop a state space model. So as per the theory of electrical engineering, first of all we write the equation of this circuit, differential equations. So how you write it? We can write down as Vi input R into IL, as current IL we have taken, plus L dIL by dt, plus here C, I can see voltage across capacitor C. Vi equals to R into IL, L dIL by dt plus Vc. So we write equation number 1. Now our purpose is to develop the state space model. As I told you that number of energy storage element, you will see how many energy storage elements are L and C, they are energy storage element. Why? Because if you see the inductor, we can write down for this inductor VL equal to L dIL by dt. This is equation number 2. So CL L dIL by dt, that shows the energy storage IL. So now we have got first state variable IL. Second, current flowing to this capacitor, so IC, which is same as here IL, we can take it as C dVc by dt. This is equation number 3. So we found that IL and Vc, these are the states. So IL and Vc we consider as state variables. And finally our purpose is to write the equation in terms of x dot equals to ax plus bu. That means when I am writing down these equations, that is it should be in terms of Vc and IL. So what we can do now? So from equation 3 we can write down as dVc by dt equals to 1 by C into IL, because your state equation equals to x dot equals to x, that is whatever x will come, that is your model will be, if you take any variable x1 dot x2 dot, you will get here x1 x2. So here IL we have already got. Now we write this equation 4. Now coming to the equation number 2, in equation number 2 we write dl by dt equals to 1 by L into VL. So we will find that here we will get VL, but our state is VC. That means this particular part VL we have to write down in terms of VC. So how will write down in terms of VC? That means we can write down as, so here we will find that this part equals to VL. So VL equals to VI minus RI into IL minus VC. Therefore, what we will write, this 1 by L, this is VL, we can write down as input VI minus R into IL minus into VC. Why we have done like this? Because here we have got VL and our state is in terms of VC, state is in terms of VC and IL, so only VL, so we want VC, that is why we have original differential equation, that is why we make adjustment like this. This is VI, this is VR, VL and VC, so VL we write in terms of VA and VC, so VI R into IL into VC. So now we write equation number 5. Now what we want? We want a state space model. So what we want, what we can do, we will write this as VC dot, this is dVC by dt, and here IL dot, and now this is VC and IL, that is x dot AX. Now VC dot equals to, see here VC dot equals to 1 by C into IL, that means the part concerned with the VC 0, the 0 into VC, what is the IL equals to 1 by C, here 1 by C written, and what is the IL dot? IL dot, this is IL dot, this is VC dot. So IL dot, that is equal to, concerned with this here VC into 1 by L, that means minus 1 by L into VC, then here about IL, so minus R by L, so we write minus R by L plus, you see here VC dot equals to 1 by, so 1 by C into IL, so we write 0, and here IL dot, here in terms of input voltage, so input is 1 by L into VA. And now what is the output? Your output is Y, that is equals to VC. So VC means here we write 1 0 VC into IL, and what about the input? Input is D is 0, so we can write D 0 into VI input. Now this is the your state space model of an electrical circuit, which is simple in nature, which involve resistor, inductor and a capacitor, and taking two energy storage elements, and we have got, this is the state space model, and we see this is X dot, this equals to A, this A matrix, this corresponds to B matrix, then this C matrix, and D is 0 matrix, A B C D matrix. So this is the one example I have taken. Similarly, different example we can try, and we can develop the state space model of the plant. In earlier we have also determined the transfer function model of such type of circuits, but transfer function if you determine, you will get a second order, but at the state space we will get only the first order system. So whenever any system is given to you, you have to see the energy storage element, then formulate the equations and develop the state space model of the plant. But many times what happened, if you are getting some differential equations, in the differential equations there is need to develop the model, that means there are no physical variables are involved. So that means some variables wish to be assumed which is not the actual variables. So from that variables we can also get the performance of the system. Therefore, the study of all these type of different variables we will going to study in the next class. Now, these are some references. Thank you.